constructive correlation by
who MP is, but we will hear about machine learning approaches to jet quenching.
So thank you. So we should be done by 10:30 for coffee. Okay, good. Listen, yeah. So somebody in going to politics told me that before they went to Washington, they were enthusiastic. Then they became skeptical, and then they became cynic, and then they are skeptical again. I went the actually opposite way. I was kind of a cynic, then skeptic. Now I'm a little bit optimistic. Although I hope I will not make too many people angry in the room because of my talk. Actually, it's good because many of those things that I picked up, authors of those things are in the room. So if you want to shoot at somebody a hard ball, please, I list the authors there. So this is it's interesting times because very recently, actually, Google engineer got fired from Google by essentially making a comment that he had a conversation what seemed to be like a 4-year-old, and that 4-year-old was actually a machine. So Blake Lemon says system has perception of and ability to express thoughts and feelings equivalent to a human child. And then he got fired. So now he either was right and he got fired because they didn't want to send a message, or he got fired because he was wrong. Look, this is I just saw it somewhere, and I thought it's good to say that you see 1950, yeah, that's long before me. The term machine learning was coined, so that's pretty interesting. And you see, from 70s to 80s, kind of nothing really was happening. They call it even AI winter, whatever that means. And then you see, since 2000, deep learning accelerated by GPU development, and then these new milestones like 2017 in models actually in production, and then 19 well-financed startups leverage machine learning. Well, and this now actually one of the biggest trends in machine learning is actually automation and no-code machine learning. So basically, you will really see putting blocks of things by people in order to design a model and bring it to operations right away. I think we're not there yet. I think we're somewhere here, and it's just the beginning.
Is that your office?
Yeah, don't say anybody at that that office looks like that. It's maybe my machine learning thoughts maybe at the moment. Yeah, I think that's a good description. So this is my machine learning thoughts and understanding. So no, I don't think there's windows here, but we should rapidly move beyond the proof of concepts. Okay, so that's my message for today, and take it home. Okay, move beyond the proof of concepts. These are not good enough, and I think most of our papers now, except maybe one, are maybe something more than proof of concept. So and I think the right direction is to go towards physics aware and really white box AI. And I don't know why you don't see what I wrote here, but let me just move it. Yes, interpretable machine learning. I think if we have to achieve this in scientific domain, otherwise we will again not do anything useful. So I think it does require a conceptual change in the way we approach or how we ask questions. So what's the question? And very often the main question is, tell me if this jet is quenched, and I take it from there and I do something with it and I study. But I think the better question is to ask is what to measure to expose jet quenching, or in a sense maximize the information on quenching. So in order to understand what maybe then to measure without using machine learning, but machine learning can help in many ways to understand things that we haven't seen in the data. Or well, there's other. Well, just to connect to Raymond's talk, I mean, there are machine learning driven developments for unfolding multiple observables at the same time. So I think this is something that we should get interested when it comes to really studying correlations of observables. Okay, and there's always this this discussion between frequentist and statistical inference. So we have simulation-based variational or Bayesian inference, which is, I think, really important. I will not talk much about it today. And I think we can constrain, we have seen this from Jetscape, but also from others, how to constrain physical model parameters with data, essentially by fitting and doing the rigorous Bayesian analysis. Now, the question that I have for this type of approach is, how do we discover missing features in the model and theory? Right? This approach will not discover to you what you might be missing in your model. So there's still place for a human scientist there. So that's good. The next topic is we need to understand how to mitigate background effects in the right way, and because machines don't understand. They learn, but they don't understand. So if you provide them with the wrong or inappropriate data, they will learn the features of that data, but it doesn't mean you will actually learn anything, or you can be misled. So I think it's important to remember that machine learning performance or performance of a machine learning model is as good as the data set itself, and it's also up to us to do it right. And machine learning performance is as good as the ML model itself. So in fact, one has to be careful, because sometimes you will start learning something about your model, not about the data, and that's so one has to be careful. Okay, important problems: how to model independent learning. And this is also what you see in many of those publications. The authors, they just basically start, they have a model, they go with it, they're trying to understand how to operate in that model space, but not necessarily always make conclusions which then take us to the data level. So this is again connecting to this data preparation. For experiments, we need to understand what the level our data, how well we understand our data in terms of, for example, efficiency. Imagine you have some parts of your detector that are less efficient than some other parts of the detector. With some inappropriate model training, you might realize you have found something interesting, but in fact it's not. It's just a detector effect. Okay, we know how to do it in standard analysis. We not necessarily know how to do it with some complicated neural nets. And again, we cannot ignore underlying event. I will not say it too many times, but even if we need to study model studies, please make sure that you have the underlying event in it, and you see how performance of your classifier, for example, changes with the fact that there's underlying event in it. Okay, suggested methodology. I think learn about the ML model using Monte Carlo. I think that's fine, but we have to learn about physics from using data, not really MC. And there are ways to do it. Okay, good note. Please take a note of this. I don't know if you're aware of this small archive, and actually small archive does nothing but points to this GitHub page. This is a living review of HEP machine learning efforts. And you will find, enormous amount of actually developments that have been done. That starts with classification, and this whole set of use of parameterized classifiers on images, jet images, event images, sequences, trees, graphs, etc. I will not read it all, but it goes from let's say LHC physics to cosmology, cosmic rays. Also, there's work on heavy ions, which does not all of them relate to. Maybe one relates to jets. Yeah, I think it's a very good resource, good literature. And then there's regression, the correlation models, and generative models, something very hot still in the field since a few years. What is also, you will also find publication about likelihood-free inference, which is very interesting for us. uncertainty quantification, and then there are some experimental results which you can find interesting. Okay, so some machine learning applications related to jet quenching problems. So jet PT correction, some of that you have seen yesterday. We can discuss the details, but that was not my point here. Is what you essentially want to try to do is to assess the PT scale of a jet found in heavy ion collisions better than previously. Okay, so this is the area-based standard deviation, how well you control your energy resolution. And then machine learning based does much better job to even larger radius, and that allowed us to go out with this new result that you have seen. Okay, there's intriguing question that people ask in our field. Is the jet quenched or not quenched, or in fact how to say which jet was quenched or what's not? And here's my yearly comment that I already said maybe before. We need to rapidly transition from was the jet quenched or not to what do we need to measure to capture or understand the jet quenching, and what was modified, how it was modified, when, where, this type of questions. Okay, it's just a very quick reminder. You will see this receiver operating characteristic curve. You will see that random classifier is right there on diagonal between true positive and false positive rate. This way will be better, this way worse, depending if this picture is rearranged, flipped, it might be going the other way. But as long as you're away from the diagonal in the right direction, you actually have a good chance to classify something. And of course, perfect classifier is here in the corner. So very early, is it 2018 already? I think. So there was this question asked, so can I discriminate quark versus gluon jets? Actual title was probing heavy ion collisions using quark and gluon jet substructure. They did a good job to use a very, the first thing you would try to do is to essentially do a multi-layer perceptron and use some observables like jet mass, two radial moments, including the girth, PTD, and pixel multiplicity, if you look at the picture. They also use deep convolutional network, again, on the images in eta phi, and then something called telescopic deconstruction framework, essentially that is able to divide, depending how many divisions you want to ask that framework, it will divide your image into either 1 or 2 or 3. Well, I let you to study the paper, but what is I think already important, and it will be a theme of some of those searches is, or exercises, let me call it like them. We find that the quark gluon discrimination performance worsens in heavy ion collisions due to significant soft event activity affecting the soft jet substructure. Well, okay, we learned something with a machine that we kind of knew, but that's fine. And then they used also Jewel and Pitya, and then they observed that consistently we find that the dominant feature of the Jewel jet quenching model is to increase the soft particle multiplicity due to medium recoils throughout the jet region. Well, okay, that's that. What worried me in that paper, so a bit of criticism, is that we observed the increase of the pixel multiplicity as a key feature in identifying quenched jets. And as far as I know, multiplicity is not really good quantity to study, especially in heavy ion collisions, right? So there's no free lunch, okay? They also see a drop in the performance in lead-lead and this telescopic feature that don't work so well in lead-lead collisions. The next one, the authors, Liliana, there she is, very good, very nice study. Here they actually use again 3 different things, so it's not like it's really impressive that people can do that. So there's convolutional networks, recurrent neural net, which is very interesting because then it can follow. It has a little bit of memory of what happened in the past. If you wish, you could play it a video and it would try to identify what's on the video. I mean, I'm not saying Liliana did that on this purpose, but then they tried to do the global dense neural network, and you see some ROC curves with some features here, and I think there was no background there, and that's a major, next step is to see how those things work in the background. So my question to the authors is also, you did not study secondary Lund plane. And my question is, was that for a reason? But if I understand jet quenching, I think there should be a lot of information about the jet quenching in the secondary Lund plane, and that would be good for the machine learning to pick up from. Okay, so some more studies. I'll move on, but then I've opened your appendix, Liliana, and this was very interesting because you show actually a correlation between deep neural nets. You show it in vacuum and you show it in medium, and then you see you correlate the outputs, and some of this is extremely interesting actually. I think you showed it like a demonstration, but it could serve as some sort of an avenue towards interpretability. Interpretability meaning, okay, so this is my output, my neural net identifies quench jets this way or with that probability, but then you can ask a question, okay, why? What is the sensitive information that my network learned about? And from there I could drive towards thinking about observable. So thanks for the appendix. I mean, no, the whole paper and the appendix. Sorry, Jesus. So the next one was from Daniel and Conrad and your collaborator. So that was very nice also. And yeah, super idealistic though, because nobody knows this one, right? Which is, so you essentially look at the vacuum energy of the jet, and after it loses energy, you compose this ratio. So that's like using all the information there is in the model, right? I understood that was what was behind it. So okay, so you looked at jet images, but you also looked at the angular distribution of soft particles and mass, jet shapes, and also groomed observables. For the groomed observables, I have to say again, remind everyone something that we did with James. So depending on where in PT you are, you have to be careful because during grooming, your reclustering sequence might be distorted. And I guarantee you that any even silly machine learning model will pick up on this, that, oh, quench jets are kind of mixed up, which is not physical. Anyway, the third thing they did, they actually looked at the geometrical aspects of jet production and then the energy loss versus traverse length. So again, they can look up constituent by constituents, how much this constituent traverses the medium divided by the PT. So this is some sort of PT weighted sum of individual patterns in the jets. Very nice, and this could enable tomographic studies. Before that, this is a show essentially how a jet looks like selected on a chi, which is this ratio of the medium to vacuum. Right, so depending where you cut, you have more modified jets or less modified jets. And then they also look at the quark jet efficiency using the same methodology. And look, here it is. It has been found that the greater the energy loss, the more difficult it is to classify the jets. And that's also sort of also how QCD works, right? It's interesting. And this is the result on the tomography points. So these are scattering points for true value of XJH, and these are scattering points for predicted XJH. So, well, it would be great to have that in an experiment, but maybe that's something interesting that one can try to understand how to use it in the experiment. Then Marta is here. They did something interesting. They went for a sequence of the splittings of a jet. And they use this long short-term memory network, which is similar to the recurrent networks. And essentially, they follow the time sequence, if you wish. and they want to classify jets, whether they are quenched or not. And here are good results for the ROC curve. And again, here we need to note that these are high PT jets. My only question is, even residual background can make your model actually do a little bit worse than it could. And my concern is basically, I'm not sure yet how to apply it in the data, but maybe I'm missing something basic. We can discuss it later. And then Xinyan, very recently, 10 days ago, you and your collaborators made this paper. This is again deep learning assisted jet tomography for the study of this thing in QGP. And the question is it possible to determine the initial jet production using the momentum of final state particles, and then to see the signal of the Mach counts? And again, how reliable is the new deep learning assisted? So they actually use something very interesting, which is essentially this point cloud representation of the data, where you can actually see distances in 3D. And if you wish, you can expand even this with additional layers of features, which can, again, you can start labeling the objects, etc. Okay, I'm going off topic, but it's very interesting technique. So, and then they study essentially the initial jet production, but this plot you have seen, oh, sorry, this is rotated. And so at zero, you see here you have a symmetric, and then depending on which hemisphere you choose, you have it symmetric. But I think this is interesting, right? This is what you were pointing to, Xinyan, yesterday, that you got a little bit off. Okay, your precision here in determination of the scattering centers is not that great, but you see it in delta phi, it's suddenly off zero, right? So that's interesting. Okay, so I have some comments. I mean, this is about this. Yes, you can do this, but with large fluctuations. So we'll have to see if we can improve this. So what was yes, the signal of the Mach count. Somewhat yes, but quantitative depth is important, and the scrutiny in the experiment. We'll have to see if we can even observe it, right? That's still jury's out. And then yes, at this point we can observe those shifts, but we need to see essentially something I also mention later. So while you get it in the model, now what is the uncertainty we should apply to this based on your model, physical model, but also model of machine learning, right? Thank you. 2 minutes, yeah. Okay, then maybe the last but not least, this is something we did, and we essentially asked the question how to make a binary classification to design observables. So you would use machine learning, and then machine learning will tell you to maximize the information in a jet, measure A, B, C. Okay, and that's very interesting. In this case, we worked with n sub jettiness, which is a minimal basis for the embodied phase space of emission inside the jet. That's the formula. And then essentially we also do it in the background. And here you see a comparison if you do lambda 1 or lambda 2 or theta g or zg. These have some discrimination power, except zg is right here. By the way, we had a discussion about zg, so not so great. But then, of course, you can go with the n sub jettiness to large values. You can have 23 times, but nobody will measure 23 times. By using essentially symbolic regression, we can identify the leading terms, and for example here for 4 terms, you still have very nice features even in the background. The advantage here is that training labels here are exactly known. Even experiment, you have PP, you have lead, you're done. You don't need to do anything. In fact, you should be able to go and do it in the data without any model. Okay, so that's interesting. The only thing is that the outcome of the particular model we use is that we get we identified some 4 terms, and maybe if we use other model, maybe these terms would be slightly different, but I think this is good enough here. Okay, so it's important to select the observables, and that's what we did with symbolic regression. Okay, I'm gonna skip those two. This is very interesting paper, but it's not on jet quenching. We just managed to teach GAN a QCD splitting function. So take a look after that and let me know. This is very interesting because from this perspective of white box, we could dissect the generative adversarial network structure and read off the splitting function, QCD splitting function. Of course, we need to go beyond the process, which is currently 1 to 2. Okay, I'm at my summary. So physics model dependent statements are the following. With some precision, we can do quark versus gluon jet discrimination in simulation. Jet quenching simulation, jet quenching information is in soft components, and in fact, as our paper shows, it's a lot of it is in the non-IRC safe part of the jet. So it's already, we know a lot of it from theory, but now we clearly show it with machine learning. And then, okay, I made my comments about geometry. Now, physics model independent statements are that there's no free lunch, okay? The model dependence is a problem that needs to be eliminated or at least controlled. When you report something, I think it would be good to, if you report what is the uncertainty quantification that you put on your conclusion. And that connects me to the third point. So my last slide is, I think the trend should be to move away from image-based deep learning to rather sequence-based data, because images will always result in some loss of information for some particular applications that might be fine. And then there are some ideas how to go for it in a different way. I would recommend to everybody to benchmark their models on a known public data sets, because we can all do it. Or we can even generate, a community-wide data set for similar to the exercises that have happened in the past. So if someone wants to work with the machine learning, we can just exactly see the performance on the same input data. Physics aware models, again, I will not repeat that. One interesting idea that crossed my mind some time ago is to really use the unsupervised or semi-supervised learning, which none of us did so far, which I think would be very interesting. And I have one slide after this. And then uncertainty inference quantification, I take a look at bias fast. This is a very new development. It's ongoing. I think it's maybe Peter can also say something about this. There might be some developments with the DOE. Okay, new directions. There's very interesting, I just want to mention this, there are decorrelation methods. So in fact, it's similar to GAN, but you are biasing against particular observables. For example, you can pick mass and you can ask your model to completely avoid learning anything about the mass, but learn about other things. And this is well, you see where I might be going with those approaches. Okay, just one sentence about unsupervised learning, if you haven't seen this, or semi-supervised. In fact, if you have just 2 points that are labeled, right, your model will go right in the middle. Okay, very good. But you can also augment this with the unlabeled data. So imagine you have those 2 jets which are from Monte Carlo. You can still throw jets from data into the same data sample, and the model might actually find different types of correlations. Of course, unsupervised learning is you don't have any model assumptions, and unsupervised learning, we just group them in some arbitrary groups. But semi-supervising will sort of try to accumulate the groups next to the data that are labeled. I think that's very interesting, and I stop here. Thank you.
Thank you very much. We have some questions. Maybe we start with Liliana and come to Xinyan.
Hi, Mateusz. Nice talk. Thanks. So let me just, so you complain about, or you pointed out that, okay, studies, we should move beyond proof of principle studies. And in our particular case, for instance, we didn't use, we throw away data because we didn't use the secondary Lund plane and we didn't use background. So to start, for me, I'm no expert in machine learning, so quite the opposite. And for me, it's not trivial to see that machine learning can help us to give an answer to a problem that is not simply a binary decision. So either it's quench or not, but we have a full spectrum. So the idea for our paper was actually to understand if there was not exactly select quenching, because we knew that we were not including background, but to see if there was some sort of bias towards the several machine learning methods that we used. Second,
can I answer the first? So I'm not asking you to withdraw the paper from the journal. No, it's there and it's good that it's there. When I'm saying we have to go beyond, that means we have to do more.
I agree.
So I think it would be nice to see those ROC curves that we see here when you do the background and you do some mitigation of the background, and you will see that these ROC curves are not so
exactly
hot
I know
anymore, right?
I know that's we agree, and we also made it I think.
And the secondary Lund plane is a fishing expedition. I don't know, maybe you tried it and it apparently was not adding new information, so hard to understand for me, but okay, I get it.
No, I don't think that we actually looked at the secondary Lund plane at the time. We just focused on the primary plane, because the other concern that we had is exactly interpretability. And machine learning, or what the output of this machine learning is, at least for me, they are completely obscure. So I want just to give exactly the minimum amount of data or features that we could afterwards withdraw and try to see if the method was actually outputting the things that we were expecting. And that's why we didn't include background. We focused just on the primary Lund plane.
It's okay.
And,
it's okay.
But I agree that this is just a proof of principles, and we need to go beyond. And for instance, background was something that, for instance, Marta just recently actually included. So I think it's fine.
Yeah. It's also, I mean, the background becomes less and less trivial when you go to lower PTs, which might be most interesting. And this is where actually Gunther's remark comes back, right? If we measure at low PTs, those substructure measurements, whether how correlated they are to the partonic shower. Yeah.
Just supplemental information. As I said, we actually, in our paper, we actually given the sort of like spread, like, the location. If we start trying to say this location machine learned predicted versus the real, the spread is 2 Fermi.
2 Fermi. So it's 2 protons over.
And then you cannot do much better than that, because the parton shower is sort of sometimes is kind of a stochastic process. And it is already.
I think you write it in the paper rightfully. You say there are fluctuations, and they are not reducible. Basically, you can't do anything.
You cannot do that. Another thing is that we find that to what is called classify whether it's quenching or not, it's very important to have a candle to compare to. So that's why we actually first we look at gamma jet, Z jet. And in our machine learning as input, not only we have the particles, the hadrons, but we also have what is the gamma direction, and that is actually very important in our case.
Right. Yeah. Experimentally, I think I see some complications with that, but maybe at Z probably easier. I don't know.
Just to tell all the people on Zoom, please go raise your hands for questions, just in case you have one.
Yeah, thank you for the very nice review. And I just want to ask a question about how to actually send the information around between series or model builder for the machine learning and the practical experimental effort, because of course we can do a lot of machine learning based master studies, but other than the take-home message from the key points, is there a way we can communicate with those model builders and really use the machine for
I think,
for practical purpose.
yeah, that's a fantastic point. And I think maybe we should actually start a hub on our own or something like this. And I think we can find this space in Berkeley if nobody else finds. I think it's important to have the same data set, for example, really for training and to see then
And
to develop
backgrounds
something.
probably, right?
Huh?
And backgrounds.
Including the backgrounds, yes. Yes,
Okay.
including the backgrounds. Thank you for this, Yenji. This was very smart.
Okay, so we do 2 more questions and then we have coffee a bit.
I think I criticized Marta. She
No.
has to say something.
Okay, this is interesting. So let's first Marta and then.
Yeah, just to react to this last one thing. So we have about 20 terabytes available at CERN for the jet quenching community. So
Ta-da.
that's not a problem. And we have kept it alive. So yeah, for the supervised learning. So I think as long as you don't put any information in which you don't have an experiment, you can always run it let versus PP, the real data, and so train your model on the data, where you of course have to embed your PP, but that's fine.
Yeah. Okay,
Yes. But
yeah,
then I
it's-
think the question is, what do you do with your output? Yeah.
that's my point.
Yeah.
That's my point. If you can't interpret and exactly know what to do, that's not useful, right?
Yes. So you have to find a way to interpret your data. So we try to do it with the loon planes. But there are multiple ways. I think it's a bit of a search, but it's not like that. Every supervised model is not useful on data.
Yes. So maybe let me rephrase. Unsupervised learning allows you to study Monte Carlo inspired models, but at the same time expand the phase space. For example, imagine that your Parton shower gives you bias jets, okay, for quarks and gluons, and they look different than in data, right? You can still throw in your quark and gluon jets without labeling them from data, and see whether they actually form 2 groups and see whether this performance improves or not. Well, for classifier, you have 2 labels, right? Marta says she wants to still have a microphone.
I mean, yes, 2 labels, you have 2 extremes, but you can have entire distributions in between. So, I mean, okay,
That will happen. Yes, of course, you will have something in between. My cartoon is by far too simplistic. I mean,
okay.
yeah.
If we
This is
agree on
not.
that, okay.
It's not like there won't be anything where the line goes, right? It's not full separation. It's never like this, by the way.
So one last question.
Thank you for the nice talk. I have a question. Are there any specific work on explainable machine learning or interpretable machine learning?
Oh, well, this is one,
Okay.
and
For example,
and this is 2, and the one before. So
Okay,
you have some reference, but in our field. But otherwise, there are many, and I urge you to go to this GitHub repository, even right now, and you will see, let's say, high energy physics driven things. There's definitely something here. Look at. Well, there's definitely somewhere here. I can't find it because the page is super long, so I was kind of
sounds good.
folding it into a fit to a slide.
All right, so let's thank the speakers again.